One sentence. That's all it took. In January 2025, one sentence from the most powerful man in tech wiped out billions of dollars in market value overnight. 15 months later, that same man reversed course so completely that the same stocks he crushed went up as much as 50% in a single week. And in between those two moments, his company quietly built something most people never saw coming. A set of AI models that just made quantum computers correct their own mistakes 2.5 times faster than before. Stick with me, because by the end of this, you'll understand why AI data center operators, not just quantum physicists, are the ones who should really be paying attention. Let's set the scene first. At CES in January 2025, NVIDIA CEO Jensen Huang was asked how far away we were from useful quantum computers. His answer was blunt. He said probably 15 to 30 years. That single comment sent shares of IonQ down 39% in a single day. Rigetti computing dropped 45%. D-Wave's CEO, Alan Baritz, fired back publicly on LinkedIn, writing that Huang had, in his words, a misunderstanding of quantum technology. It was a brutal moment for an entire industry that had spent years trying to convince investors it was more than science fiction. But here's where it gets interesting. Huang didn't just quietly move on and let that comment define him. Behind the scenes, NVIDIA kept working with quantum hardware makers, national laboratories, and university researchers. By June 2025, Huang had already softened his public position, saying quantum computing was nearing what he called an inflection point. And on April 14, 2026, a date deliberately chosen because it's World Quantum Day, NVIDIA dropped an announcement that flipped the entire narrative on its head. It's called Ising. And before we get into the eye-popping numbers behind it, you first need to understand the one problem that has kept quantum computers as expensive lab experiments instead of practical machines for almost 3 decades. Quantum computers are built on qubits, the quantum version of a regular computer bit. The catch is that qubits are incredibly fragile. Stray heat, tiny vibrations in the building, even a cosmic ray passing through the lab can flip a qubit into the wrong state without anyone noticing. Today's best quantum processors make a mistake roughly once every 1,000 operations. That sounds rare, until you realize a genuinely useful quantum calculation might require billions of operations strung together. One error in a billion-step chain, and your entire result is garbage. So engineers came up with a workaround called quantum error correction. Instead of trusting one fragile physical qubit to hold your information, you spread that same piece of information across a whole grid of physical qubits, wired together in a checkerboard-like pattern called a surface code. It might take dozens, even hundreds, of noisy physical qubits arranged this way to reliably protect just one unit of usable information. Together, that entire grid behaves as one much sturdier unit called a logical qubit. Sensors around that grid constantly check for mismatches, called syndromes, almost like a spell checker running underneath your keyboard as you type, flagging problems without necessarily telling you the correct word right away. And a piece of software called a decoder has to look at that pattern of mismatches and instantly work out what actually went wrong and how to fix it, before the next round of errors piles on top of the last one, and the whole system loses track of what's real information and what's noise. Here's the part most explainers skip, and it's honestly the part that matters most. That decoder isn't fixing things after the fact, on its own schedule. It has to keep up in real time, faster than new errors are appearing on the chip. Picture a live sports broadcast with a translator working in real time. If the translator falls even half a second behind the commentator, the broadcast becomes useless nonsense by the end of the game because the gap just keeps growing. A quantum decoder has the exact same problem, except its deadline isn't measured in seconds. It's measured in microseconds, over and over, thousands of times per second, for as long as the calculation runs. For years, the open source tool most of the industry leaned on for this job was called pyMatching. It worked, but as quantum chips scaled up to more qubits, it started running into a hard ceiling. This is exactly the bottleneck NVIDIA decided to attack head-on. And what they built to solve it? That's where this story gets genuinely surprising. NVIDIA's answer is a family of models named Ising, borrowed from a 19th and 20th century mathematical framework originally used by physicists to describe magnetism. Decades later, it turns out that same framework is remarkably good at describing the kind of error patterns you see spreading across a quantum chip. Ising isn't one single product, though. It's actually built from 2 separate tools that solve 2 separate problems. And NVIDIA is giving both of them away completely free and open source for any lab, university, or company on Earth to download, inspect, and modify. The first tool handles decoding, the real-time translator we just talked about. It comes in 2 versions, and both are tiny by modern AI standards. One has under 1 million parameters and is tuned purely for speed. The other has under 2 million parameters and is tuned for maximum accuracy. Both are what's called 3-dimensional convolutional neural networks. the same broad family of AI model that's traditionally been used to scan medical images or video frames for patterns, here repurposed to scan a grid of qubit data as it changes round after round, which happens to be exactly what a spreading error pattern on a quantum chip looks like. According to NVIDIA's own published benchmarks, at a chip configuration researchers refer to as distance 13, the speed-focused model runs up to 2.5 times faster than pyMatching. The accuracy-focused model, meanwhile, cuts the error rate down to roughly a third of what pyMatching achieves in the same conditions. NVIDIA also says its models needed about 10 times less training data to get there. Now, it's worth pausing here and being completely upfront with you. These are NVIDIA's own internal benchmarks, published on their own developer blog, not independently verified by a neutral third party. The methodology and the underlying code are open source, which means outside researchers can and likely will test these claims themselves over the coming months. So while these numbers are real, documented, and specific, not vague marketing language, the true test of how solid they are will come from that outside verification as adoption spreads. And that brings us to the second piece of Ising, which is arguably even more ambitious, and it's the one almost nobody outside the industry has been talking about. That second piece is called Ising calibration, and it tackles a completely different headache. Before a quantum chip can run a single useful calculation, engineers have to manually tune it, adjusting laser frequencies, magnetic fields, and voltage levels so that every single qubit on the chip behaves consistently with its neighbors. Traditionally, this calibration process eats up days of highly skilled labor for every new chip, and it often has to be repeated as conditions drift. NVIDIA built a 35 billion parameter vision language model for this specific job, meaning it can read charts and experimental plots the way a trained physicist would, and it's been trained to spot exactly what needs adjusting on a quantum processor. Paired with an automated workflow, NVIDIA says this can shrink that calibration process from days down to hours. On a benchmark NVIDIA created specifically for this task, called QCalEvil, the company reports its calibration model scored a few percentage points higher than several well-known general-purpose AI models when it comes to quantum-specific calibration reasoning. Again, that's a benchmark NVIDIA designed itself, so it's best treated as a strong internal claim rather than a settled independent industry ranking. Still, even skeptics of NVIDIA's marketing tend to agree on one thing. Automating calibration is a genuinely hard, genuinely valuable problem, and almost nobody had built a dedicated AI model for it before this. Numbers on a slide are one thing, though. What happened just weeks before this launch is where the story stopped being theoretical and started being proof. A company called Quantinuum used a related NVIDIA interconnect technology called NVQ-Link to run a live demonstration on their Helios quantum processor. Their system needed to react within 2 milliseconds to keep pace with the chip's error correction demands. Their actual measured reaction time came in at 67 microseconds, more than 30 times faster than the requirement, with plenty of margin to spare. NVIDIA and Quantinuum both describe this as the first real-time demonstration of a particularly demanding class of error correction, known as QLDPC codes, running at that kind of speed on real hardware. That's not a projection. That's not a simulation running on a laptop somewhere. That's a working system, measured with 2 named companies putting their reputations behind the result. And once that kind of proof became public, Wall Street didn't wait around to figure out what it meant. On the day of the Ising announcement, quantum computing stocks didn't just tick up, they exploded. IonQ jumped just over 20% in a single session, closing near $36 a share. Rigetti Computing climbed more than 11%, closing near $17 a share. D-Wave Quantum and Quantum Computing Incorporated both posted double-digit gains as well, with some reports putting D-Wave's move as high as 16% that day. By the end of that same week, some of these stocks had risen as much as 50% from where they started just days earlier. Financial analysts started calling it the NVIDIA halo effect, a nod to the exact same pattern investors had already watched play out in AI chips a few years earlier. The logic is simple. When the world's most valuable company plants its flag somewhere, the market tends to treat that as a signal the technology just crossed a line from speculative science project into something worth building an actual business around. It's the same instinct that once turned a niche graphics card company into the backbone of the entire AI industry. If you're a little surprised these numbers moved so violently in both directions over the course of just over a year, you're not alone. And if this kind of deep dive into what's actually happening under the hood of the AI and quantum world is useful to you, tapping the like button genuinely helps more people find this instead of the surface-level headlines. Now, back to the part of this story that most of that coverage got wrong. But before you assume this means fault-tolerant quantum computers are right around the corner, let's pump the brakes for a second, because this is exactly where a lot of headlines got ahead of themselves. Experts differ sharply on what any of this actually means for the timeline. NVIDIA itself is not claiming Ising solves quantum computing outright. The company's own framing is narrower and more careful than that. Ising removes two specific engineering bottlenecks, calibration and decoding, while dozens of other hard problems, like manufacturing more physically reliable qubits at scale and driving down the underlying hardware error rate itself, remain largely unsolved. Even the earlier public friction between NVIDIA and quantum computing CEOs is a reminder that this industry doesn't fully agree on its own timeline, let alone its own definitions of success. Some reports suggest genuinely useful, large-scale, fault-tolerant quantum computers could still be several years away, even with tools like Ising already in place. So the honest, balanced framing here isn't quantum computing has arrived. It's closer to one of the biggest engineering bottlenecks in the field, just got meaningfully smaller, with real hardware demonstrations to back it up. And that distinction actually connects directly to something much bigger already happening inside AI data centers right now, which is the part of this story most coverage completely missed. Here's why this isn't just a quantum computing story. It's a story about the data centers already running today's AI models. NVIDIA didn't build Ising as a standalone science project, living off in its own corner of the company. It's designed to plug directly into the same Q2Q software platform and the same NVQ-Link interconnect that link quantum processors to NVIDIA's GPU clusters. NVIDIA's own stated vision is that future supercomputers won't be purely classical or purely quantum. They'll be hybrid quantum GPU systems where quantum hardware handles specific kinds of simulation that classical computers are bad at, and GPUs handle the massive parallel workloads they're already good at, with both talking to each other in real time over that same low latency link. More than a dozen major supercomputing centers across the United States, Europe, and Asia have already signed on to this NVQ-Link architecture, including national research institutions like Fermilab, Lawrence Berkeley National Laboratory's Advanced Quantum Testbed, and Brookhaven National Laboratory. That means the same data center infrastructure already being built out for today's generative AI boom is quietly being future-proofed to plug in quantum hardware the moment it's ready to contribute. For anyone running, designing, or investing in AI infrastructure, that's not a minor footnote buried in a press release. It's a genuine hint about where the next decade of compute spending might be heading, and it's worth watching closely. It also explains why the list of early adopters for Ising reads like a who's who of the quantum computing world. Atom computing, IonQ, IQM quantum computers, Inflection, Academia Sinica, Harvard's John A. Paulson School of Engineering and Applied Sciences, the UK's National Physical Laboratory, IRO-Q, Conductor Quantum, and multiple US national laboratories have all started integrating these tools within weeks of the announcement. When that many independent, often directly competing organizations adopt the same open source foundation almost immediately, it tends to mean the tool is solving a real, shared, painful problem rather than just generating a flashy press release. QCTRL, another quantum infrastructure company working alongside NVQ-Link, reported early results showing a 50 times reduction in classical computing overhead and a 5 times speed up in overall wall clock time for certain calibration routines, which lines up with the broader story NVIDIA is telling. None of these companies are obligated to sing NVIDIA's praises, and several of them compete directly with each other for hardware customers, which makes their shared willingness to build on the same foundation more meaningful than any single benchmark chart. If any of this sounds familiar, it should, because NVIDIA has run this exact playbook once before, and it's worth spending a moment on why that history matters here. Back in 2006, NVIDIA released something called CUDA, a free software layer that let ordinary researchers program NVIDIA's graphics cards to do general-purpose math, not just render video game pixels. For years, most of the tech industry treated it as a niche tool for a small group of scientists. Then, over the following decade, CUDA quietly became the invisible foundation underneath almost every major AI breakthrough, from image recognition to today's large language models, simply because NVIDIA had spent years making sure the software layer was already there, waiting the moment the rest of the world needed it. Ising and NVQ-Link look a lot like that same strategy. Applied to quantum computing a decade or two earlier in the technology's life cycle, NVIDIA isn't trying to build the quantum chips themselves. Companies like IonQ, Rigetti, IQM, and Quantinuum are still the ones doing that hard physical engineering. What NVIDIA is doing is making sure that whichever of those companies eventually wins the race to build reliable, large-scale quantum hardware, they'll already be running on NVIDIA's software and NVIDIA's interconnects by default, because that infrastructure got there first and became the path of least resistance. That strategy also hints at why the practical stakes here go beyond stock charts and benchmark slides. If calibration and decoding stop being the bottleneck, the industry's attention shifts toward actually running useful quantum algorithms, things like simulating new drug molecules, modeling battery chemistry, or optimizing complex logistics networks, all problems where classical computers genuinely struggle as the complexity scales up. Nobody serious is promising those breakthroughs are imminent, Most researchers in the field describe useful, large-scale quantum applications as still requiring more reliable qubits, better error rates at the hardware level, and years of continued engineering, regardless of how good the decoding software gets. But removing a software bottleneck does tend to speed up how quickly the remaining hardware problems get attacked, simply because researchers can spend less time fighting their tools and more time testing actual ideas. It's also worth remembering that pyMatching itself, the tool Ising is being measured against, isn't some outdated relic. It's still an actively maintained, well-respected piece of open-source software that much of the quantum research community trusts precisely because it's been tested and scrutinized for years. Beating a mature, battle-tested baseline by this margin, on paper, is genuinely impressive. But mature tools earn trust slowly through years of real-world use across many different labs and chip designs, not through a single benchmark chart on launch day. Ising is only a few months old at the time of this video. The coming year, as independent labs run their own comparisons on their own hardware, will tell us whether these numbers hold up exactly as published, or whether real-world conditions chip away at some of that headline margin the way they often do with brand new tools in any field of engineering. So where does that leave us? NVIDIA didn't invent quantum computing, and it certainly didn't magically erase the decades of hardware challenges that have slowed this field down since the very beginning. What it did was take two of the most stubborn, unglamorous engineering bottlenecks in the entire field, keeping a quantum chip properly tuned, and correcting its errors faster than they can pile up. And through the same AI techniques already reshaping every other corner of technology directly at them, backed by real, published, reproducible numbers, and at least one live hardware demonstration, to prove it wasn't just a slide in a keynote. Whether history looks back on this as the exact moment quantum computing tipped from lab curiosity into real infrastructure, or simply as one very solid step on a much longer road, is something we'll only really know by watching what gets built on top of it over the next few years. Either way, the bottleneck that was supposedly going to hold this field back for another decade just got a lot smaller, and that's not nothing. If you want to keep watching that story unfold as it happens, go ahead and hit subscribe, because given how quickly this field is moving right now, this is very likely not the last time NVIDIA's name comes up in this conversation.